So good day, everyone. My name is Oladipupo Sennaike. I'm from the Department of Computer Science in the University of Lagos. And I'll be talking about discovering connections in open data sets. So let's go on to, we said open data portals, right? So I think it's very important to start with open data portals. There are things that most likely we have interacted with at one time or the other when we need to get information about, a country, a state, at a point, governments thought that it made a lot of sense for them to be able to make this data available, to the general public so that we can be informed, and more importantly, perhaps there can be services that can be built on these data sets that are made freely available. And so today we have a lot of data portals. We have for Nigeria, in fact, even within Nigeria, I think there has been an effort from Edo State and I think Kaduna State to have data portals. It would be nice for every parastatal to be able to have that. The US government has its own data.gov, UK has its own. We know the World Bank open data also. So we have these all available, and basically they are online platforms that provides access to a collection of data that is open, that is freely available, and that you can always reuse. All right, so it has there's a general architecture for open data portals. So usually you have three major layers. You have the user interface, you have services, and then you have storage. And there are different data portals that are frameworks that are available out there. So this is very generic. And of course, each of the components of this will be offering some service, one service or the other. So you have user interfaces for the catalog, search, analytics, visualization, for example, right? And you actually have APIs that you can also interface with so that you can be able to pull data from the data portals, and a whole lot of other things. And importantly, you also have the catalog and the services. One of the very important things is, if I'm going to be using APIs, then it means that the data I'm going to be using should be machine readable, for example, right? So you should be able to do that, manage your data sets, manage users, description about the data that you are putting on the data portals, you should be able to manage it. So you have your metadata management. You should be able to do search, query, log, and so on like that. And then the last layer is the storage layer, right, where we actually basically store our data. Okay, so we move on. So we have different open data platforms. One of the very popular ones is the CCAN, right? But we have other ones. And CCAN is one of those ones that I've actually also interacted with in the past, right? So those are data platforms. Why open data portals matter? Yeah, for transparency and accountability, something we really need in our environment. For example, we want to have citizens that can access government spending, for example, budgets, public projects, and so on like that. We should be able to have a place where we go and get that information. We should be able to have people, or developers that can actually use this to build solutions, right? So innovation and entrepreneurship is one of those things that can come out of having open data portals. Of course, in research and education, something like we did, for example, is one of those other things, right? And not just for the sake of research, we should actually be able to do it so that, for example, we can actually influence policy at the end of the day. For the longest time, I didn't know how important policy was until I got involved with, the AI research lab, for example. And I realized that sometimes you could actually be doing a lot of things, and then it will never come to life just because policy is against it, right? And so you cannot leave policy alone, and say that, no, let them do their thing. No, we have to be, parts of that policy-making process, and nowadays, more and more, policymakers are realizing that they need to make their policies based on evidence, right? The evidence will come from the data you collect, and the way you analyze that data, right? So that's also very important. And so governments can also be able to provide better planning with the data that they get from, these data portals, right? So it's an avenue for them to, see how they can harness the insights they can get from these data portals so that they can better provide transportation, and agriculture and every other sector. All right, so we have these data portals all over the place. As at the time when we were doing this research, what happened was, while they provide very basic search capabilities, I can actually go to a data portal and say I am looking for data on, say, budgets, or parks, or I want something on buildings. I can do that, and it gives me, a lot of data sets. And then the task I'll have to do is start looking at those data sets myself. It doesn't tell me how these data sets are related. Suppose I'm interested in one particular one. It doesn't tell me that these are data sets that are also speaking, to this theme that you are searching for, So they have such capabilities and features for filtering search results, but they don't have provisions for recommendations of unrelated data sets. Now, if I have knowledge about related data sets, it means that I can decide how I can put these data sets together, whichever way, you understand, because they are related, so I can be able to make inference, from them. And then these data sets themselves, there are a lot. I mean, for data.gov, for example, it's over 350,000 data sets, And then for UK government, you have over 55,000 data sets, right? So, there was a project in Ireland, right? And basically they had this challenge. The initial thing to do really is to say that, look, I can have metadata on this data set. So one of the things we can do, whenever you upload a data set, you can actually have tags to them, right? So that you tag them, but apart from tagging them, some people can go ahead and then have descriptions of the data sets, Of course, some other metadata which is not usually obvious are things like the field names of the fields you have for that data set, and so on like that. So you have a number of things about the data set. So the challenge was, we want to be, whenever we pick a data set, there was actually a project that requires that we want to see related data sets. And the question is, how do we do that? Should we just match the tags, and then that should be it, It doesn't seem to be, very complete, when you do that. And so the people doing the research thought that it would be nice to have another way, of doing this. And so we got in contact at a point, and I felt that, there could be, some way. The reality is that there have been ways that people have been doing this. I've described, the fact that you can use metadata, for example. I can use the tags, but it's not okay. And then one of the approaches that they actually initially wanted to use was to say that, look, when you are uploading data, is it possible for you to actually indicate which data is related to this, so that it becomes easier? Well, okay, so for a start, it may make some sense, right? But as it grows, it becomes impossible for you to do. So there has to be an automated way, of doing this. So we have some approaches, right? Lexical-based sources approaches, for example, using WordNet. You can actually do some things on it. So we have some of these technical things, the LDA, the ESA, and so on like that. Those are some of the ways that had been used to try and do things. And basically what this is trying to do is that I have this data, can I see how it is related? So usually all of them will have one way of measuring how, the similarities between one data set and another. All right, so our objective here is to determine how we can get the implicit relatedness. We call it relatedness. Now, how one data set is related to another. So we want to have a measure of how they are related, and then we decided to use a self-organizing map. We'll talk about self-organizing maps, very shortly, because we thought it was, a tool that, naturally fits into what it is that we are trying to do. And in fact, so in the past, I had worked with self-organizing maps. In fact, in doing my PhD, I worked extensively with it. And that's why I got contacted for this particular project. All right, so I'll basically talk about this very briefly. So it's an unsupervised artificial neural network. I'm sure we know what artificial neural networks is. That's the basis of a number of things that is going on today. Generative AI, for example. It's basically an artificial neural network itself is basically a model that tries to mimic the way the brain works, right? So the brain works by having neurons that are connected, right? And then they take inputs, they process that input, they give an output, but then they are massively connected, and they also, after giving an output, they have ways of adjusting the connections between one neuron and another, right? And the adjustment of that connection is what enables learning, you understand? And basically that's what a neural network is. It's actually not more than that. Okay, so there are a lot of mathematical things going on behind, but then the model, the artificial neural network tries to model the workings of that natural, neuron, right? The way our brain works, in a mathematical way. Now, when we do that, the ideal thing will be that, so it means that if I have a data set, for example, that I have labeled, right, I can say that, let me present this data set to my neural network that I have built. It's a connection of all those neurons in some ways. And then let it give me an output, right? When it gives me an output, I can tell it whether it's right or wrong, right? And then when it tells me it is right, then it means that what the connections, are okay, I can strengthen it towards the right direction. If it is wrong, it means that I need to go and adjust my connections, so that the next time I give it that input, it should give me the right answer. That's putting it very generally, right? But that's the idea behind what you call supervised learning, right? I have data sets, I have labeled them, right? And I can say that, look, when you see this particular data set, this is the label you are supposed to give. So adjust yourself, right? You adjust yourself through the weights, right? The weights are the ones mimicking the synapses between our natural brains, right? Adjust it so that it can actually, get that result correctly. Again, this is very simplistic, but that's basically how it works. So when I have labels and I give it data sets, then I say it's supervised. When I don't have labels, it means I just have data, and it can still learn from me, then I say it's unsupervised. So what does that really mean when I don't have any label for this data set, yet I'm expecting my neural network to learn from it, The supervised is usually very straightforward. Now, for unsupervised, it works in I'm sure, I don't know, we know what clustering is. Clustering is trying to group things that are similar together, For our self-organizing map, it works in a similar fashion, right? And so the difference is that it discovers those clusters itself, right? A number of clustering algorithms, you have to say that, look, I have 5 clusters in this data set. Whether you are right or wrong doesn't matter. But by the time you finish, it's going to fix your data set into 4 seeds into those 5 clusters. You understand? That's basically what clustering algorithm does. But for our self-organizing maps, it doesn't. In fact, the reality is that we don't call them clusters like that because they don't have hard boundaries around them. You just know that whenever I have a self-organizing map and I have 2 data items that are firing two nodes that are close to one another, it means that they are close together. You understand? That's basically the concept. Some will go to the same node. So we have the unsupervised artificial neural network, and basically what it does is it takes high dimensional data. I mean, a number of times our data set will have a lot of fields, right? A lot of attributes, you know. And what our neural network, our SOM does is that it takes this high dimensional data that has all these attributes, right? And then projects it onto a two-dimensional map. So our neural network, our sum is basically a two-dimensional map of neurons, you know. So it's like I have a grid of neurons, you know, all like that. We'll still go on to see it, right? So it does that projection from that high dimensional onto that low, and then very importantly, it preserves order. That preservation of order is what allows us to actually be able to say that this data set should be related to the next one close to it. You understand? And that's the order. So at the end, the sum itself is an array of units of nodes, two-dimensional array in this case, right? And they can be regular, rectangular. I mean, so I can actually, you can imagine having a two-dimensional array of squares, you know, each square is a node, right? Or it can be hexagon, right? Each hexagon is a node. And then each node has itself an associated n-dimensional vector. You know, I said we are presenting data to this network, right? To this two-dimensional grid. Now, each node on that actually sees the data, right? Each node sees all the data. So if I present a data set, I'm not presenting it to one node, I'm presenting it to all the nodes, right? So if my data set has 10 attributes, for example, it means that the node should see all the 10 attributes, right? And that's what the N is talking about here, you know, those 10 attributes. So I see the self-organizing map sees the data sets, you know, it sees all the attributes, and then it's able to, you know, project that data set onto itself. Okay, so I have, okay, this scattered debate, it was supposed to be underscore, right? Each node, right? Remember I said for a neuron, it has synapses, you know, that it adjusts. And then mathematically in the neural network, we use what we call weights, you know, to do that. We could just call them weights. I call them model vectors here, right? And so if I have a node that is looking at a data set of n, each node must have n model vectors also. Does that make sense? You know I'm a teacher, so sometimes. So it has n model vectors. So it means that if I have, let's go to the next slide. I think we should be able to. Okay, so if I have these n data items, right, then it should be able to look at the data itself with the n model vectors. The computation is something like, oh, this data set, which is usually numeric, right? So we'll still get to where we have to transform all our data to numeric. So the data item, the first attribute is 1, right? That attribute will be fed to a particular model vector, right? An element of that model vector, multiply with it, and does some transformation. He aggregates that across all the data items, right? So that it gets a value at the end of the day, right? Basically, that's what it does. So you have your data set, you have for each of the neurons that you have your model, which you call your weights, you know, that is, you know, matching that data. So if I have a 10 by 10 sum, for example, it means that each one will have that n number of models, and then the 10 by 10 will have each, you know, n number of models each. You understand? So the algorithm basically is competitive, right? So we have our data that is presented. At the end of the day, by the time we match our data and we transform it with our model vector, there's a value that is gotten, right? And so we will say, out of all these values that my 100, you know, nodes have gotten, which one matches best? You know, the one that matches best is we call it the winner. And basically what we do is that the one that is winning, we ensure that the next time this data set is presented to it, right, it even does better, it gets a better value. And then the other ones that did not, win, it weakens their connection, for that data set, and it does that by adjusting that model vector, either increasing it or reducing the value of the model vector. Basically, that's where it works. Usually, we use the Euclidean distance, to be able to do that. And then the model vectors of the best units and its neighbors are adjusted so that they can always be closer to the inputs. So we just have a slight pictorial view of what it is we've talked about. So this is our data set. These are model vectors, the weights, right? And so the weights are all attached to this, So the weights of ij is, for a particular one, and, remember it has n. Each of them will have n model vectors, each of these, So it's looking at these inputs, it's doing some computation with the weights, and at the end of the day, it gets, an output on the map, right? So this is our self-organizing map itself. And so if this guy, for example, is the one that actually fires, it means that he's going to make sure that the next time, he adjusts the way to make sure that he even, responds better, and then adjust the ones around it, you understand? Basically, that's what it is. And so the ones around it, we call it a neighborhood. And we can decide on the neighborhood size. So we can say it's just, the ones immediately around it, neighborhood size of 1, right? Or it should be neighborhood size of 5, The effect of this is that at the end of the day, by the time you present the data and he has learned, these nodes will be a representation of the data itself. You understand? That all these nodes, right? And we expect that if you have a node here, the data set around it are close to it, They are connected one way or the other. They are similar to it. They are related to it, And that's the property we try to use here. So basically what our job has now been reduced to is to say that, so if I have my data portal, and I can actually extract the data, from that data portal, I can go ahead and form a self-organizing map, which, if you look at it, is a two-dimensional array, isn't it? Right? So I represent all these data sets with a two-dimensional array, and I know that that array each node will be telling me, that I have this data set or data sets that is for me, and the ones around me are close to me. You understand? And so that's the idea here. So let's move on. So basically, we had to go through, the normal process of ensuring that we have a methodology, right? So we have our data preparation, right? We have to go to the data portals, and get the data we need to be able to work with. The data we are working with is basically text, So, like we do in NLP, we need to transform that to a vector. Remember that our input to our self-organizing map is a vector, right? A series of numeric values, That's basically what it is. So we have to find a way of doing that, right? So we used the TF-IDF there, and then we train our sum. Training our sum means that we are presenting our data, to this self-organizing map, and then it is adjusting, the weights, over and over again. I must mention that this can be iterative, do it until you get to a point where you say, okay, we call it converged. Again, one of the things we did was we don't have an idea of what to expect from these data sets. So we decided to experiment with different sizes of our self-organizing maps, right? And so that we'll be able to get what is optimal for the representation of that data that we are looking at, And so we did that. We had measures to be able to say that, look, this is better. One thing we always need in when we are doing research is a metric, something that you can be able to measure and say that this is actually better, at that point. So we had some metrics, and then we actually applied it. Because this project was done in the context of a bigger project, and the bigger project was to be able to have a framework where people can search and be able to get related data sets, we actually went ahead to incorporate the solution, right, into that bigger project. Next slide. All right, so what data set did we get? We got data sets from, so the project was done in a research institute called Insights Research Institute for Data Analytics, and it's located in Ireland actually. And the data set was from the Dublin Open Data Platform. They call it, Dublin. So it provides the information on the number of activities in the Dublin region, from sculptures in public parks to pedestrian footfall and so on like that. And for that particular data set, it had at that time 255 open data sets published by different government parastatals. In fact, one of the ways they thought they could do it initially was to say that, look, it's not so much. Each parastatal should just go and label their data set properly and then try and find how related it is. And from what I heard, they said, who is going to pay? Who is going to pay for that activity? Of course, the project cannot pay for that. Next slide, please. So that is the data set. And so what we did was to, using APIs, we were able to get, the data, the metadata, the content of the data portal, from there. And then we also did some name entity recognition also to be able to extract entities like persons, organizations, and locations from the data set that we had captured. All right, so this just represents some of those things that we were able to capture. So we had title of the data set, the organization that actually gave it out, the theme, notes, tag. The tag is supposed to be able to help, but then, when things are explicitly done sometimes, and when it is in this kind of scenario, it becomes very difficult for you to enforce people to make sure that they do those things correctly. It has the source fields, the location, person, organization that we extracted, from those data sets. And so what did we do to this? What we did was to transform it, into a term matrix using the TF-IDF. Basically, same thing you do in natural language processing, where you try to look at, the words that you have in a document, and then try to do some transformation on it, so that at the end of the day, we know our text documents are very variable. Some can have 100 words, some 10 words, and the content itself, the terms I use can be very varied, right? So basically what we did was to say, we know we can transform this into something that is fixed. We transformed it into a matrix that is 255 by 1241, so it becomes regular. And then of course all the items that we have there, we've made sure that they were numeric at the end of the day. So all those words, we had to find a way of making them numeric. And so our input to our sum was our document term matrix, right? That's basically what we gave to it. Like we said, we didn't have an idea of the kind of sum we should do. What size should it be, right? So we actually had to experiment with different map sizes. Our model was selected based on so we had metrics again. We had something called topological error, and we had something called quantization error. The topological error is actually the proportion of input samples for which the first and second best matching units are not neighbors on the map. So it tells you that, look, you have looked at this data, you have mapped it onto this sum, but when we check, right, if you have a high topological error, it means that these items that you have mapped on this map, they are not as similar from the source data. You understand? That's basically what it is. And then quantization error is the average distance between the input data and the model vector of its best matching units. So this indicates how well a map represents your training data. So based on that, we had some, did some maps, so that we'll see how I mean, we did a lot more than that, but just in simplicity. Again, because of the topographic error, this basically means that, remember we said you can consider the neighbors, right? So this was, the neighborhood of one, it and just his neighbors. But then he also has neighbors that are, so we can actually increase the neighborhood. Basically, what we did here was to increase the neighborhood to see how he also behaved, right? Okay, so unlike supervised learning, if I want to check if I'm correct, I just say that, okay, so I give you some test data, and then when I give you some test data, I'll check if you are right or wrong, and then the number you get right, I can mark it and say, oh, this is your accuracy. You understand? I mean, I can have a measure, very easy measure. I've told you to learn something. I now want to test you. I give you 10 tests. You got 9 out of it. So your accuracy is 90%. You understand? Very straightforward. But remember, we didn't have a label data here, right? So what we had to do was say that, look, we have gotten this map, I have this node that contains this data set, and the next node to it contains this data set. Can somebody that understands, this data come and see if this makes sense? That's basically what we had to do. So we got domain experts to come and look at what categories has been discovered by the map, and validate that, yes, these categories are actually things that are sensible. Let me also make a confession. So when we did the map, and we got an output, and I sat down to look at it, it made no sense to me initially, So I remember taking it to the guy that was in charge of the project and say, this is what I got, and then this is what we can see in this data. And the guy was very excited. He was like, fantastic. I was like, I can't see it. So he was trying to explain why parks and recreation should come together, why culture, and, he was, trying to explain those things. So those are the kind of insights they were able to get, right? So, so for a category, what we call a category, remember we said it's a self-organizing map. It doesn't have hard boundaries, so I'm not drawing, boundaries around my data sets. What a category will mean now is that, okay, so if I present this data set to this map, which is the best matching node, right? If I get the best matching node, that is the category is going to fall into, right? I can now consider that node, and maybe I can decide to say, okay, let me have a neighborhood of 1 around it. All data sets is in that I can refer to a category. Again, we did not try to impose, a hard cluster around it. We just wanted to know that, okay, this is the nodes. These data sets that fall to these nodes are all related to one another, right? So basically, that's what that is. So in all cases, the domain experts were able to infer that the concept being addressed by each of those categories, even when you increase that radius, slightly, makes sense, that they're actually valid categories. Okay, so this is just a pictorial view of the map. So because remember there are data sets that are hard, so what we basically did was to number the data sets, the 255 data sets, so that if I see a data set 176, I have an index somewhere that I'll be able to point to that data set. So I know exactly what this is. So this is a representation. So at the end of the day, note, once the training maybe takes a few minutes, but once I've trained it, and I have this, I'm fine. I can represent this in very efficient, data structure, so that I can be able to, say that I have this data set that is 133. Can I know the ones that are related to it? The ones that are related are obviously the ones around it. You understand? Basically, that's basically what it is. So this is a 20 by 20 sum. I mean, this is a heat map just to show that, okay, this has a lot of data items that are, on it. This has less. And then the same thing goes for the next one. So this is basically the same thing, in another graphical form, just to show the distribution of the data that we have presented to that data to that map on the sum. Right? Here we decided to say that, look, if is it possible to just have some other insights on our data? So we did some word cloud on some nodes, so not on the entire data set now. Just say that, so if I am on this node, right, what is the data actually talking about, And we did it for both on the metadata, the original data that we used, and on the transform data itself, you understand? So we had that to be able to say, okay, so this is looking at culture, and heritage, you see it very bold, so it's able to see arts, Yeah, the next one, same thing, but this is now based on the node features itself. So if I have a node, what data, is speaking to that node, not the metadata now, the data that we've gotten, right? So basically, we did that, and made a lot of sense. Next slide, please. Okay, so how did we apply it? So on the interface where you are supposed to go to Doplink and search your data, for your data, what we have is, once you search for something, so you search for lower, data set, it gives you a list of data sets. I can actually decide to say that, so this data set that you are giving me, can I see the neighbors, right? This is what shows the neighbors. So basically, this means that these items are close to it on the map. And there's a slider here. I don't know if it's the slider is basically used to increase or decrease the neighborhood, you understand? So as you increase it, it increases. As you decrease it, it decreases, right? So basically, that's how we are able to use our data sets, our application, our research, so we were able to incorporate it into the larger project, and so we had related data sets. So we were able to look at the sum-based model for computing semantic relatedness among data sets in that catalogs. And then, so the results shows a strong evidence for the efficacy of the approach. So we can actually reveal what data sets are related and then what are not. Now, so you can actually address challenges such as poor quality of metadata, because people don't want, but then, the poor quality of metadata may affect the effectiveness of our approach, because we relied on the metadata. So basically what we are saying is that we are relying on the description of whoever described it, his judgment in naming his fields, and so on like that. That's what we are relying on, possibly, if we can say that, look, rather than looking at just the metadata, can we look at the content itself? Make more sense. A lot of things will not change, but then there's also a challenge, because a lot of these data items are not, textual, right? So if I want to show you budget, it's all numbers, so it becomes another challenge, that's another work, And then, of course, we were hoping to do this with to large data catalogs. And then, so this is also a way of making sure that we can integrate, we can have tools that can integrate, data sets that are compatible.